In this lecture, we'll introduce the concept of message integrity along with a cryptographic primitive called message authentication codes. Until now in this course, we've been concerned with ensuring secrecy of communication between a sender and a receiver. But what about the goal of integrity? Roughly speaking, this means that we might want to ensure that a message received by the receiver originated from the intended sender and was not modified in transit. Note that here we're explicitly concerned with an active attacker who can modify things sent between the sender and receiver, as well as inject his own traffic to be received by the receiver, looking as if it came from the other party. And we're concerned here in ensuring that any messages obtained by the receiver came from the intended sender with whom it shares a key. Note here that standard error correction techniques are not enough, because we're not concerned here with random errors in what's sent from the sender to the receiver. We're concerned here with an attacker who can decide exactly where and how to modify what's being sent between the parties. And the right cryptographic tool for ensuring integrity in the symmetric key setting is called a message authentication code. At a high level, the way a message authentication code, or a MAC, works is as follows. So as usual in the private key setting, we have a sender and receiver who have shared a key K in advance. When the sender wants to transmit a message M to the receiver, what it will do is it will compute a tag T by applying some MAC algorithm to the message M using the shared key K. The sender will then transmit M and T across the channel. And what we're trying to achieve is the following. If we have an attacker who can modify what's sent and replace it with some arbitrary message M' and tag T' of the attacker's choice, then the receiver, when trying to verify correctness of the tag T' on the message M' using the shared key K, should find that the tag is not correct. Verification should in that case return 0, indicating an error. In contrast, if M and T, as sent by the sender, were received unaltered by the receiver, then verification should return 1, indicating that that message did indeed originate from the sender. Note here that there's no concern of secrecy at all. In fact, as depicted here, the message M is sent in the clear. As usual in the private key setting, there are two canonical sort of applications where message authentication codes might be used. The first is when we have two parties sharing a key who are separated in space. And here I've shown as an example a user interacting with their bank. So here the user and the bank share a key K in advance. The user is transmitting some message M to the bank and wants to make sure that the bank receives that message unmodified. As an example, if the user is sending a message to transfer $100 from its own account to someone else's account, then the bank should receive exactly that message, and if an attacker changes that message to reflect a transfer of $1,000, the bank should detect that something went wrong and that that message did not originate from the intended sender. The other canonical application of message authentication codes are when we have the same party authenticating some communication separated from itself over time. And here we can imagine a web server holding a key K and generating a cookie which will be stored on the client side. The server wants to make sure that the cookie it receives back at a later point in time from that user has not been modified. So what the web server can do is to generate a key K that it will store. It can then authenticate the cookie using a message authentication code and send the cookie along with the tag to the user. At a later point in time, the user will send that cookie along with the tag back to the web server, and at that point in time, the web server can verify the message authentication code to check whether or not the cookie has been altered. Why might this be important? Well, imagine, for example, that the cookie encodes some information about the price of some item. And if the price of that item is 10, say, then it would obviously be very bad if a malicious client could modify that and change the price embedded in the cookie to, say, $1. Let me stress here that secrecy and integrity are orthogonal concerns. As depicted in the pictures, in these cases we're only concerned with integrity and we're not concerned with secrecy at all. Again, the message is being sent in the clear. Now, of course, that doesn't mean that you can't have both secrecy and integrity, but for our purposes right now, we're going to treat them independently, because in general it might be desirable to have one without the other, right? You might want secrecy and not care so much about integrity. You might want integrity but not require secrecy for what you're communicating, and so we'd like to study them independently of each other. One thing I'd also like to point out is that just using encryption and using that, as it were, as a sort of a tag, does not in general provide any integrity whatsoever. This is related to an issue we've seen before, the issue of malleability. It's not precisely the same thing, but the fact that we have encryption schemes that are malleable indicates in particular that those schemes don't provide any integrity. And we can see an example of this very easily. So imagine if, as it were, that we were trying to use encryption as a form of message authentication and sending a ciphertext alone, and assuming that if the ciphertext decrypts properly, then it must have originated from the sender, and if not, then it's an error. Well, imagine very simply that we instantiate the encryption here by the one-time pad. So that means that the shared key k is an n-bit string. The message here, let's assume, is also an n-bit string. And the ciphertext is just the XOR of the key and the message. Well, if an attacker intercepts that and just flips the final bit of the ciphertext, then at the receiving end, the receiver will just decrypt that to the same original n-1 bits that the sender sent, with the last bit being flipped. If you work out the math, this is exactly what you get. And from the receiver's point of view, there's no way to distinguish whether the sender indeed intended to send this message m1 through mn-1 and then mn prime, or whether that was caused due to some interference from an adversary. In particular, the one-time pad, in the one-time pad, there's no way to get any error upon decryption. Any n-bit string is a valid ciphertext, and so it sort of should be clear that the one-time pad is not providing any sort of integrity protection at all. What this means is that even a strong security notion like perfect secrecy does not imply any integrity whatsoever. Formally, a message authentication code is defined by three probabilistic polynomial time algorithms: gen, mac, and verify. The key generation algorithm gen takes as input the security parameter and outputs a key k, and as usual will assume that the length of the key is at least n bits. The mac algorithm takes as input a key k and a message m, and outputs a tag t, and as we saw in a previous slide, will denote that by subscripting the key and writing t equals mac sub k of m. In general, it's possible to have probabilistic mac algorithms, but we're going to assume, for simplicity and for convenience, that the mac algorithm is deterministic. And as we'll see, most commonly used macs are in fact deterministic. The verification algorithm takes as input a key k, a message m, and a purported tag t as input, and outputs either 1 or 0, with a 1 indicating acceptance and a 0 indicating rejection. And of course, the natural sort of correctness condition is that for all messages and all keys k output by the key generation algorithm, if we verify a tag generated by mac using that key, along with the message m, then we should get 1. This just means that if the honest parties are communicating without any adversarial interference at all, then whatever the receiver obtains from the sender will verify correctly. Now, as far as defining security, it's sort of lucky that in contrast to the case of private key encryption, there's really only one standard definition of security for message authentication codes. The threat model here is what's known as an adaptive chosen message attack. That is, we assume that the attacker is able to induce the sender to authenticate arbitrary messages of the attacker's choice. And the security goal is existential unforgeability. That is, the attacker should be unable to forge a valid tag on any message that was not explicitly authenticated by the sender. It might be easier to understand this in terms of a picture. So here we imagine that an attacker can interact with the sender, influence the sender, or induce the sender in some other way to generate tags on messages m1 through mi of the attacker's choice. So we imagine that the attacker can specify a message m1 and then receive back the tag t1 computed on that message, and so on for a total of I times, thereby obtaining the tags on I different messages of the attacker's choice. After doing so, it should still be infeasible for the attacker to come up with any message M' not equal to one of the messages M1 through Mi, along with a valid tag T', that is a tag for which the verification algorithm run by the receiver would output 1. You can ask whether this definition is too strong. When would it be possible, for example, for an attacker to arbitrarily choose what sort of messages the sender authenticates? And similarly, it might be the case that if the attacker can output a valid tag on some arbitrary message, it doesn't really buy anything, it doesn't really get anything for the attacker. However, the important point is that we don't want to make any assumptions about what the sender might authenticate, and we also don't want to make any assumptions about what forgeries are meaningful and which ones aren't meaningful. In general, those kind of determinations are application dependent, and what we'd like to do is, just as in the case of our definitions of private key encryption, come up with a strong enough definition such that a scheme satisfying that definition can be used anywhere. And it's true that a MAC satisfying our definition of security can be used anywhere integrity is needed without having to think about the semantics of the underlying application. Formally, we define security for a message authentication code as follows. We imagine fixing some message authentication code pi, and if we also fix an attacker A, then we can define based on those a randomized experiment that I'll call forge. So forge depends on A and pi as well as a security parameter n. And the experiment works as follows. First we generate a key k, and then we allow the attacker to interact with a MAC oracle. This oracle just allows the attacker to specify messages and get back the corresponding tags computed on those messages using the key k generated in the first step. We can then let capital M denote the set of messages that the attacker has submitted to this oracle. Finally, A outputs a pair M, T, and we'll say that A succeeds and the experiment evaluates to 1 if and only if the following two conditions hold. So first of all, it should be the case that the tag T output by the attacker is a valid tag on the message M. That is, that verify sub k applied to M, T should output 1. Also, it should be the case that the message M on which the attacker output its tag T should not be equal to one of the messages for which the attacker already requested a tag from its MAC oracle. Of course, if we drop that condition, then it would be trivial for the attacker to always succeed by simply requesting a single tag on a single message and then outputting that message along with the tag that it received. So to prevent those kind of trivial attacks, we have to enforce that the message M output by the attacker is not in the set M of things whose tags it's already obtained from the oracle. And then in the usual way, we can say that a MAC pi is secure if for all probabilistic polynomial time attackers A, there is some negligible function epsilon, such that the probability that the forge experiment outputs 1 is at most epsilon of n. So note here that in contrast to the case of encryption, where we require the success probability of the attacker to be at most 1/2 plus epsilon, here we don't want the attacker to succeed any of the time, and so we bound the probability of success by epsilon. That means it should be infeasible for the attacker to ever output essentially ever output a valid tag on a new message. One thing I want to highlight about the definition is that replay attacks are not prevented. A replay attack occurs whenever the attacker simply replays a message transmitted by the honest receiver. Because of the way we've defined things, and in particular because we've defined MACs to be stateless, there's actually no way we can hope to prevent them. Right? The verify algorithm cannot distinguish whether it's been given a message M and a tag T that it's seen before, because we don't allow the verify algorithm to maintain state. Now, this does not mean that replay attacks are not problematic. And in fact, replay attacks are often a significant real-world concern. If we go back to our example of a user interacting with the bank, if the user requests for $100 to be transferred to the attacker's account, well, if it uses a MAC, then we know the attacker can't change the $100 amount to $1,000. However, if we don't take any precaution to defend against replay attacks, then what an attacker can do is simply replay that request to transfer $100 10 times, and thereby achieve the same effect. So there is very often a need to protect against replay attacks. However, any such protection must occur at a higher level of the protocol. It can't be done by the MAC itself. It has to be done by something which is maintaining state and is aware of the semantics of the messages being authenticated. In the next lecture, we will begin our study of message authentication codes by constructing a very simple secure MAC for short messages.